everyone's trying to get online at the same time.
I noticed that with I was trying to watch some chemistry videos that he posts to Moodle itself, that's like YouTube, and sometimes it doesn't let me watch them. Like it sits.
Yeah, it's weird, and it's, I think, hard to win. Okay. Well, Haley, you can keep using your, I'm assuming you're attached with your phone if you want, but I have this live on YouTube, so if you need to watch the video later, you also can. Okay. Let's jump in to the presentation. Okay. So we're going to talk about strength, hardness, and elasticity in metals. We're going to introduce each one as well as compare hardness to toughness. And then we're going to finish discussing elasticity a little bit. We kind of introduced it with Young's modulus on Wednesday, and we're going to sort of finish out our discussion today. Strength is the ability of a material to resist deformation. From Wednesday, who remembers what the definition of stress was?
Stress, it's a force applied.
That would be the strain.
Internal resistance.
Yes, it's the internal counterforce to strain. Okay? So if strength is the ability of a material to resist deformation, and stress is the counterforce to that load that's put on it, how are these different?
So what's the question?
How is strength different from stress?
Strain, that's like without it forming, like that's so resist, be able to resist deformation, stress, it gets built.
You said didn't you say all metals deformed, or no matter how light the load or how strong the metal, something happens?
Yep, there is at least some deformation regardless of the load. Obviously, they can resist some, like we talked about the example of the legs of this desk and the load of the feather. Right, there's some minimum.
I don't know.
Stress is impossible to measure. Sure, you can't directly measure stress, but we have a pretty good representation of it. And similar for strength, we have a pretty good representation of it. But that's a good thought. What else? Just in the wording of those definitions. The ability of a material to resist deformation and the internal counterforce to a load, to strain.
What is the ratio between the two?
What about it?
Well, there's going to be a ratio between the two, and where they, oh heck, I don't know, where they meet is where everything changes. I don't really know.
Okay. Strength is a measure of the maximum load that can be borne before failure is apparent. So essentially, when we're talking about stress, we have a spectrum where we can experience elastic deformation, and then plastic deformation, and then our yield point, and then our maximum tensile strength, and then finally fracture, right? And we can go through this whole range of stress due to our changing strain, because that material has the ability to have some elastic deformation, right? And it can yield, and then eventually fractures. Strength is talking about a maximum load before failure is apparent. So when we're comparing degrees of strain, where does failure start to become apparent in a metal? Hayden.
I can't remember what it's called now.
Is that
When it's like at that yield point.
Yeah, the yield point. That's what it's called. At the yield point, that elastic deformation starts yielding the plastic deformation, and we start to see permanent damage to the metal, right? And then we get all the way to maximum tensile strength, and from there, we fracture. And that's a definite failure, right? So we start to see this after our elastic deformation. So strength is essentially saying the load, the maximum load, before our stress can no longer resist failing, okay? It's the maximum stress the metal can sustain. So they're not quite a ratio, Joe, but they are defined in terms of each other. What's interesting about strength is that it will vary based on the type of load, right? Our stress and strain relationship always has that little linear divot and then hyperbolic graph shape, right? That's always the case. But based on the type of load, metals can essentially have different strengths in different directions, right? So if you think about back to when we made our models of our crystal structures, having the face cubic or the body centered cubic or that hexagonal closed pack, there's directions that you have more or less atoms in, right? And so in the same way, you can pull, push, or shear your metal, and they'll find different weak points. And so each of those types of loads, a tensile stress corresponding to a tensile strength, a compressive strength, which is the maximum compressive stress that a metal can carry, or shear strength, which is the maximum shear stress the metal can have before deforming, failing, sorry. All describe different maximum loads from different stresses, right? And they're all going to be talking about finding kind of those weak points in the different metal structures to exploit in a particular style of load, okay? So, strength is always qualified by the type of stress. When we say strength, we might be generically talking about this definition, that it is the maximum stress that a metal will sustain. But when we actually have a value for a particular metal, we have to say if it's tensile strength, compressive strength, or shear strength. Okay? Because each one of those loads does something slightly different to the metal, so its strength has to be qualified. So, you guys have probably heard these words before in terms of talking about our metal. What do you guys think tensile stress is, or tensile strength?
How much it can resist being pulled apart.
Exactly. And compressive? Someone online? Being squeezed, pushed together, exactly. And shear.
It's the maximum strength it can stand being pulled from two directions apart.
Pulled from two directions. Also, sometimes, if you think of a length of pipe, it's the perpendicular, right? So you've got two trying to push it in half. So, I have actually been taking a class on how to teach better, and they had some ideas for some ways to not just give you guys theory. So we're going to try a couple. So grab a piece of paper. Everybody online, grab a piece of paper also. I want you to draw some sort of pipe or piece of metal under tensile, compressive, and shear stresses. What does it look like to see those stresses in action? I just realized I wasn't sharing the screen for our folks online. Okay, everyone online get a chance to do that? Okay, anyone online want to turn on their video and show us what you came up with? Hold it just a little higher, Jennifer. Anyone else? Okay. Everybody in class. You guys all come up with something similar to this? We pulled apart our block or pipe. We shoved it together with some forces. Maybe you had a pipe rigidly attached to some asphalt and you dropped something on it. Okay, and then shear. You're going perpendicular in two different directions here.
What's your strength word for that? That's something else.
So if you drew, this has a force this way because it's connected to something, and you're putting your force here, and you're expecting it to shear right here, then it would work. See how that changes it just a little bit? Where the direction of the two forces are going in opposite directions.
Yeah, this one was like a bend.
Yeah, and so, you know, if I kicked this, where there's a bend here, and I was trying to shear it off of this,
Oh, okay.
right?
That's a similar like holding it right here.
Yeah.
Kick it this way.
If you know, you held the table really, really securely and I kicked.
I don't know if I could hold it to, what is it, judo kick.
Okay. Hey, Kyle. Thank you for letting me know. Tell me again at the end so that I remember to change your attendance. Okay. So, everyone online, this is kind of what you had. Okay, cool. So, from strength, hardness is the property of a material that enables it to resist plastic deformation, penetration, indentation, and scratching. So essentially, all of the mechanisms of wear that would occur on a metal. Okay? If we have friction, if we have something scraping against it, scratching it, attempting to corrode it, flowing past it and trying to erode it, or that area of plastic deformation where we're not worrying about failure, but we are worrying about misshaping temporarily. Hardness resists these. So Strain is that load that we put on the metal. Stress is its internal resistance to that load. Strength is the maximum stress before we have failure. And hardness is the resistance to plastic deformation and wear. So they're all very similar because they're all how well a metal holds up in our environment, but they're all just slightly different properties of what we can do to a metal in a reactor environment, okay? Hardness is important because resistance to wear generally increases with hardness, okay? So the higher hardness the metal has, the more likely you're going to be able to be in a friction or erosion, corrosion, or drop environment without causing damage to your metal, okay? Toughness and hardness are hardness and toughness are very similar, but they're just a little bit different. So if hardness covers all these things we just listed, penetration, indentation, scratching, plastic deformation, erosion, corrosion resistance, all those types of wear, what would you guess toughness is? Joe.
Well, based on what it isn't, the toughness would be the resistance to actual fracture? Or is the fracture going to be included in what happens to hardness?
Hardness, we're generally not talking about getting close to fracture, right? Because we're in that elastic deformation range. So I see why you're making the two comparisons, especially when we talked about like strength and stress, but it's not quite. If I pointed out that all of these types of wear are slow mechanisms that occur over time and repetition, does that give you guys a different idea what you think toughness might be?
And it would be the resistance to fast actions against it.
Like what? What would be a fast
A car wreck.
car wreck? And what's the word for the type of force that happens when a car rams into something?
Well, that would be plastic deformation.
Not quite. Haley's got the word I'm looking for here. Sudden impacts, okay? So if you have some sort of sudden mechanism, some sudden force that comes and hits that metal, toughness is going to be our resistance to that mechanism, okay? It's defined as the work required to deform 1 cubic inch of metal until it fractures. So Joe, when you were thinking along the way of this including fracture and hardness not, that was correct, right? Hardness, we're talking about, we're resisting elastic deformation. We have a slightly lighter load, but slowly over time, all those mechanisms are going to cause wear. And as the metal wears, it then does not have as much stress to be able to resist the strain it's under, right? That internal force gets degraded, and its yield strength is going to lower, and its ultimate tensile strength is going to lower, and it will fracture sooner, even though the mechanisms that are interacting with hardness are not creating the fracture, right? Toughness, we're going to put work into the metal suddenly, like an impact, right? Until we fracture a small part of it. Toughness is tested with something called the Sharpie test, and it is named after a person, so it's spelled not like the marker, the Sharpie test. Can you guys see that? Everybody online, can you see the board at all? It's a Sharpie test. And we're going to see the machine in the materials lab that they do this with, even though they're not going to demonstrate it for us. They essentially, okay, well, I put it in chat so you guys can see how it's spelled. They essentially take a very heavy, very tough metal, and they create a point on it. And then they lay a thin sheet of whatever metal they're testing across the test stand, secured at the end. And then they drop that pointed hard metal weight into it, and they see how far they dent into the sheet of metal. And when they deform a cubic inch, that amount of work, so that energy of accelerating it, gravity fed, or sometimes they have actual pumps that accelerate it, they can calculate how much work they put into that force moving it down, and they know the toughness of the metal. So whenever you need to think about toughness, I think the test machine they use for this is the greatest illustration. You're just driving a point suddenly towards the metal you're interested in, okay? So it's that work to create a sudden impact that actually fractures a small piece of the metal, right? So in the nuclear industry, when we have shipping containers, have you guys all seen the video of radioactive material shipping container getting dropped on the pole, right, to test it for accident analysis? You guys seen that?
Yeah, we're supposed to watch it.
Those big casts? I just assumed that you would have seen it in 151. No? Okay. Well,
I watched one where they're train cars.
yeah. So the big shipping casks, the big huge ones that store our spent nuclear fuel, they have to be able to be lifted up by a crane. I think it's 10 feet, 9 feet, somewhere in there. And then there's a 1 meter or 3 foot pole about the size of the skinny traffic cones, right? The ones that aren't really cones, but are more rods. But it's metal with a pointed end, and they have to drop the shipping cask onto it on its weakest side, so the bottom, and it has to not penetrate the shipping cask. To simulate if there was a car wreck while they were transporting this and it rolled off and struck something, you can't damage the shipping cask. So the toughness of the metal in our shipping casks has to be high enough that that sudden impact does not create any fracture. Okay. So now we've talked about toughness, hardness, strength, stress, and strain. On Wednesday, we talked about Young's modulus and how elasticity is that ratio between stress and strain in that linear region on the first part of our tensile graph, right? That was what it is. Conceptually, it refers to the rate at which a given metal is able to distort its size and shape under a range of stress and strain forces and other varying factors without crossing the yield point into permanent deformation, right? So elasticity is its ability to distort and still be able to recover if that force is removed. So we're thinking about structural materials. Say, what is required to hold our core in place during a seismic event? Do you think we want high or low elasticity? I want everyone to think about that for just a minute, and then we're going to vote. Yes, please.
Talking about like the needle on the seismograph? On a seismograph?
No, I'm talking about like the actual steel struts that anchor our reactor vessel into the ground so that when there's an earthquake, it doesn't roll over on its side and split open. So structural materials, metals, structural metals. Who votes high? Joe,
That means,
Caden?
like, you can move, bend more.
High elasticity, yeah. So more ability to distort. Haley does. Sam does. Okay. Who says low? Jennifer says low. What do you think? Patel, high or low? Okay.
Seems like you'd want a lot more elasticity, but you have to have a certain amount of strength.
You'd want a balance. I mean, up to a point, you'd want elasticity.
Okay. Okay. So we're getting there. So it was a little bit of a trick question because it's a false dichotomy. Because the answer is it can depend for exactly some of the reasons you guys said, right? Sometimes, Haley pointed out you don't want, or Jennifer pointed out you don't want the metal bending, right? Sometimes we want really rigid structural material with very low elasticity and very high toughness. It's going to not allow it to distort, but it's going to have a very high tensile strength. So that range after elastic deformation, before our ultimate tensile strength, that's where we want it to exist. It's rigid and it holds something structurally secure. But sometimes we want to be able to handle loads without having plastic deformation. We want to stay in that elastic region, and having a high elasticity helps, right? Even if it means that we have some structural changes under those loads and stresses. So this is especially the case when you have some sort of cyclic stress and you can deal with a little bit of deformation. So in the design of our electrical lines, right, that you see out there, especially here in Idaho, where they can go for miles across these huge mountains before they come to another town, those are hanging, one, with the weight of gravity, and two, we have pretty significant temperature swings between winter and summer here, right? So summer, high elevation, they don't have a ton of protection from the sun, they heat up and they expand a lot, right? And then winter comes and you've got the cold temperatures and those wires contract. And so one of the reasons that they typically still use wood, one is cost, but also they can make those joints so the supports can give a little as the metal pulls them or as they're released because it lengthens, right? So if you think about that application, you want a little bit of elasticity. It'll bend in the winter when it is contracting, but then when the load is gone, it'll be able to go back, and you've built in a range that it can remain structurally sound as it adjusts to those loads, right? So there may be times where we want elasticity in our structure. Typically, nuclear structures, we don't want deformation to be occurring, right? We want something that is going to be very rigid and structurally sound, and we're going to try and distribute our loads so that we're not creating much distortion or deformation, right? So we'll put in extra supports and extra metal and extra thickness so that we're not anywhere close to fracture, but we're also not having as much distortion. But even then, we go between several hundred degrees Celsius and shut down where it might be room temperature, right? So all of our metals are going to have some cyclical lengthening and contracting just due to heat, right? So in a lot of spaces, if we want to ever be able to shut down our reactor and not have to buy a bunch of energy to keep everything hot, which sometimes we do. Sometimes we keep things hot even if we're shut down, if we're going to be shut down for a short amount of time to avoid cycling. But we want to be able to handle that and have some elasticity in our metal, right, for those normal cycles. But we don't want like that level of swing we just talked about with telephone poles in our systems in a nuclear power plant. We just don't. Does that make sense? Why sometimes both? Depends. Okay. So here's a list of some of the metals that are typically used to alloy with other metals. They're often mixed into steel in certain percent to do different things. So when I read to you what we're changing in an alloy, I want you guys to kind of explain to me what nickel does, okay? Nickel will raise toughness and ductility. We didn't talk about this one. because it's just not as important in nuclear, but raising toughness without raising hardness. What does that mean? A metal with higher toughness, but not increasing, or sorry, raising toughness, but not hardness.
Takes more work required to deform it for fractures for nickel added, but it's still the same. The hardness is still the same in that alloy.
Okay.
You're gonna raise its resistance to sudden impact, but not its resistance to denting or scratching.
Exactly. So if you have an application where this is going to be under a very high fluid flow, where there's a lot of risk of erosion, is nickel what you want to alloy your metal with?
I wouldn't think so.
No. If you needed to make a cask that could survive a drop onto a pole, would you want to add nickel to your metal, to your alloy? Yes. Chromium reacts with steel to form a carbide. This is a particular type of chemical reaction that happens there that increases the hardness of the metal. Okay? Essentially, the chromium atoms go into certain locations in that crystal lattice, and by entering that lattice where they do, they make the lattice more resistant to the force that hardening deals with. Okay? What does chromium added to an alloy do for us then? Someone online. So why would you add chromium to a steel? Someone online. It does become denser, but specifically when we're talking about it becoming harder, chromium hardens the metal. What applications would we want to add chromium to our steel alloy for? High pressure, yes, that's a good one, right? So hardness, right? We're talking about this sudden impact, right? So high pressure is going to be something that's consistently putting a force against your metal, right? Constantly stressing it. Okay. Or where scratching is a concern. Yeah. So if you have the opposite of nickel, right? You've got a pipe that's in a lot of flow, you've got worries about erosion, or Jennifer said that high pressure, you've got a constant force that's constantly pushing out on the metal because you've got a pressurized system. Chromium is a good choice for making our steel alloy good for that application. Okay. Copper, pretty much like nickel, okay, raises toughness, but not the hardness. But what it does is it doesn't form a carbide and replace atoms in the crystal. Essentially, it joins in between and it prevents those atoms from dislocating out of the crystal structure. Okay? Molybdenum hardens a steel, but minimizes grain enlargement, right? So we talked about the fact that our grains are the pieces of a light crystal, and they're pushed up against other grains along a grain boundary, and that the grain boundary is the area where we have to worry about particular types of corrosion, right? So when we can harden material substantially, but minimize grain enlargement, what are we doing to that steel alloy? What are we making it good for?
something that needs to resist scratching because it's visible and part of a look, but is also under stresses.
They're gonna be broken apart to use the frame. They're gonna allow it to break apart. Use the frame.
Will you say again which large grains are bad for cracking resistance? The
Large,
larger the grain.
large grains are more prone to corrosion and stress corrosion cracking. So molybdenum is added when you want a material that's going to be in an environment with a lot of wear properties that also cannot corrode. The molybdenum is added to nearly all of the seals put inside a reactor because it will reduce this corrosion substantially without sacrificing hardness. And it is, yeah, high heat, because then we got, when we cycle that heat, right, we've got a constant wear load, right? That is correct, Jennifer. Okay. Stainless steels have 12% chromium, at least, right? What did we say that chromium does? Increases hardness, right? So compared to a pure carbon, a stainless steel alloy with chromium is much better for what kind of applications? The wear resistance, right? So anything that attacks the hardness. So Jennifer worked at a solar power plant where they used a moly chromium piping for the fluid that the mirrors were pointed at to put them at high heat. Yeah, Jennifer, that's exactly the kind of application, because when the sun goes down and you don't have that heat coming off the mirrors, you're going to have that metal contract, and then it's going to expand when it heats up. So there's a constant force going on there, right? There's a wear load, and you've got fluid moving through it, and it's going to be heating. So there's going to be some aspects of turbulent flow. So it's going to be rough, and you're going to have issues with erosion inside that piping system. And that chromium and molybdenum together, they're going to have a lot of resistance to erosion, corrosion, and other wear type of forces that are happening on the metal. So that's exactly why you add moly and chromium. Okay. Any questions on that? Does that kind of make sense when we look at the properties of metal, and then we look at the materials that we can alloy metals with and how they affect those properties, how we get to selecting the particular alloys we want in a nuclear power plant? Even if you don't necessarily know how to go and make that selection, you understand how someone who needs to make that selection would think about it. Okay, cool. So, as a reminder, LEL 117, 8 a.m. on Monday. We're going to observe a tensile test. I think it'll be great for you guys to see that. No, you don't have to be in the careers class. We are going to go over the resume. So if you want feedback on your resume before you submit it, Haley, be in class. But if you are comfortable with your resume and ready to submit it for the assignment, you don't have to solicit feedback.
Did you get my email?
Mm-hmm. Yep. And I have yours ready to go over in class. Okay. Well, that is it for today, guys. See you in the next class. But see you for materials Monday in Lily Grid. Okay, Kyle. Yeah, go ahead and send it. We'll go over it. in class. And then let me change your attendance for this class. Yes, thank you for reminding me. Oh, thank you, Amber.
Do you have a class in here next?
I do. Yep, I've got the first years. Okay, all right, guys. You're both here for attendance and not absent. Okay, see you guys later.